In this section, we will talk about GRE and mGRE. A GRE tunnel provides connectivity to a wide variety of network layer protocols by encapsulating and forwarding those packets over an IP-based network. DMVPN, guys, uses multi-point GRE, mGRE encapsulation and supports dynamic routing protocols, which eliminates many of the support issues associated with other VPN technologies. GRE tunnels are classified as an overlay network because the GRE tunnel is built on top of existing transport network, also known as an underlay network. Additional header information is added to the packet when the router encapsulates the packet for the GRE tunnel. This new header information contains the remote endpoint IP address as the destination. The new IP headers allow the packet to be routed between the two tunnel endpoints without inspection of packet's payload. After the packet reaches the remote endpoint, the GRE headers are removed and the original packet is forwarded out of the remote router. Let's now have a look how we can configure the GRE. In here we have two routers, network router 1 and the network router 2. To configure the GRE tunnel, the command is interface tunnel and, for example, tunnel 0. Then we assign an IP address to our tunnel. For router 1 we are assigning 10.10.10.1, and for router 2 the IP address is 10.10.10.2. Make sure that we are using /30 subnet masks for both. Since GRE is an encapsulating protocol, guys, we adjust the maximum transfer unit MTU to 1400 and maximum segment size MSS to 1360 bytes. Because most transport MTUs are 1500 bytes and we have an added overhead because of GRE, we must reduce the MTU to account for the extra overhead. A setting of 1400 is a common practice and will ensure unnecessary packets fragmentation is kept to a minimum, guys. Then we also defining a tunnel source IP address in here, so that's the IP address of this interface, and tunnel destination is the IP address of the remote router's GIG00 interface, as you can see in here. And the same MTU and MSS values are configured on the R2, and this time tunnel source is surely GIG00 again of the router 2, and the destination is this time the GIG00 of router 1. And then we are just making an OSPF configuration in here to advertise the 16 and the 10.10.10 networks and 17 and the 10.10.10 networks. Let's go ahead with the NHRP. Next hop resolution protocol, NHRP, guys, is defined in RFC 2332 as a method to provide address resolution for hosts or networks for MBMA networks such as frame relay and ATM. NHRP, guys, provides a method for devices to learn the protocol and MBMA network, thereby allowing them to directly communicate with each other. NHRP is a client-server protocol that allows devices to register themselves over directly connected or disparate networks. NHRP next hop servers, guys, let's type in here. You can see them as NHSL as well. NHS are responsible for registering addresses or networks, maintaining an NHRP repository, and replying to any queries received by the next hop clients, and you can see them also like NHC. The NHC and NHS are transactional in nature. DMVPN uses multi-point GRE tunnels, which requires a method of mapping tunnel IP address to the transport IP address. NHRP provides the technology for mapping those IP addresses, guys. DMVPN spokes, which are NHC, the next hop clients, are statically configured with the IP address of the hubs, which are the NHS, so that they can register their tunnel and MBMA IP address with the hubs. When a spoke-to-spoke tunnel is established, NHRP messages provide the necessary information for the spokes to locate each other so that they can build a spoke-to-spoke DMVPN tunnel. The NHRP messages also allow a spoke to locate a remote network. So when it comes to the NHRP message types, guys, we have 5 different NHRP message types, and they are registration, resolution, redirect, purge, and the error. Let's have a look of now how NHRP works with multiple GRE. Okay. On screen, guys, we have 2 spoke routers, and they are spoke 1 and the spoke 2. These guys are establishing a tunnel to the hub router, as you can see in here. Later, once we look at the configurations, you will see that the destination IP address of the hub router will be statically configured on the spoke routers. The hub router will dynamically accept spoke routers. The routers will use an NHRP registration request message to register their public IP addresses to the hub. As you can see in here, spoke 1 is establishing tunnel to hub. I'm using public IP address and my public is 2222. And spoke 2 is also sending an NHRP registration request message and sending the public IP in here, as you can see. On the second step, guys, the hub, which is our NHRP server, will create a mapping between the public IP addresses and the IP addresses of the tunnel interfaces. So here is the message of the hub, and he's saying, great, we have 2 spokes. Okay, that means I received your registration request, and I'm adding their public IP addresses to my NHRP cache. And NHRP cache, you can see that 1.2 is mapped to 2222 and 1.3 is mapped to 3333. And here is the 1.2 actually, this, and here is the 1.3. And after a few seconds, guys, spoke 1 may want to send some packets to spoke 2. Then it needs to figure out the destination public IP address of spoke 2, so that means it will send a NHRP resolution request asking the hub router what the public IP address of spoke 2 is. So you can see in here is the NHRP resolution request, and he's saying, I want to send something to spoke 2. Can you tell me what public IP address they use, their hub? Then hub will use surely its NHRP cache. to answer this query. On the next step, as I told you, the hub router will check its cache and finds an entry for SPOC2 and sends the NHRP resolution reply, as you can see in here, and will say that sure, you can reach them at 3333, and here is the entry that is in the cache that hub router uses to reply for the SPOC1's request, and this is the NHRP resolution reply packet. Now guys, anymore SPOC1 knows the destination public IP address of SPOC2 and is able to tunnel something directly. This is great, right? We only required the hub to figure out what the public IP address is, and all traffic can be sent from SPOC to SPOC directly. And from now on, if SPOC1 wants to send some packets towards SPOC2, it will not go to the hub anymore, and it will just go from this way to this way directly.